Yeah. Thank you very much. You already on? So remember match filter. Now I think there are two versions on the of videos. Right? Let me write down a few things, then we'll start. So let's look at this problem. Autoregressive moving average or ARMA processes. So it's a mouthful of words. So there are two special cases of this also, AR or autoregressive processes. And there is also moving average processes. So the best way to introduce them is to specifically show you what we mean by this. So if xn, so we are dealing with the discrete time processes. If xn can be expressed in terms of its own previous coefficients, so xn is sometimes you see a sign here, minus sign. But also minus of AK are the new coefficients, BK, whichever way you want to write. So look at this. The current value, if you think of this as a stochastic process, one realization, then any current value linearly depends on previous n values. Like, look at here. This is n minus k, so n minus 1, n minus 2 up to p values, 1 through p. So 1 to up to p, previous p values, and some white noise disturbance. So if a process can be modeled like this, we call it, so this is a regression on itself. That's what auto means. In other words, the regression is not on y. What is regression? The current value being laundered using the previous p values. So this is where the regression is going on, previous p values. So you can say this has got a p-step memory, if you like. So if a process can be represented like this, then we call it an autoregressive process. Then the question is this white and stationary? Does it have a linear time invariant representation, etc.? Let me also write down what is moving average. So if xn can be written as sigma bk So this is the moving average portion. In other words, look at what it says. So if I write, if this is some process W of n, right? Then what it says is at any point n, look at what it says. You take any point n, then take a window of size. What is the window size here? Q plus 1, right? Including, right? So remember, and then simply average it, right? You're average. Look at, you're only averaging the W values, because think of these are all equal for a minute, equal to 1 over Q plus 1. Then this is just a running average, right? So you move forward, the window moves with you. So that's why we call it move. Stock market, you do this all the time, because the stock values may be too erratic depending on today's weather or somebody died or whatever. But if you smooth it, this is smoothing, right? If you smooth it, you may get, so if you average it out, you may get a much smoother process, and that's this one. Remember, this is the smoothed version of W, whatever it is. W doesn't have to be white noise. So if you want, you can also write this like this, right? Whatever is the process, the current value plus Q previous values. So the notation to this is, you generally say this process is an MAQ process, and this process is a ARP process. P. And if you have processes where you have both the representation, in other words, if xn can be written as minus sigma ak x of n minus k, k equal to 1 through p, plus sigma bk w n minus k, k equal to 0 through q, then we call this to be an ARMA process, because it has got both the pieces.
Are those, you have two W's there, are those the same process?
No, I mean, remember previously I wrote here it as W0, I mean 0 through Q, right? If I pull the 0 out, then this would, if you want to be precise, this would be B naught. When you put K equal to 0, you get Wn. So I just took one term out, right? So I should have kept the B naught here. So you can either write it like this, or you can leave it the way we wrote it before. So this will be 0, right, through Q. But if you want to take out the 0 term, only thing I just wanted to show you that you can write it like this, right? Wn term. But there the remaining terms are regression on itself, whereas here it's a moving average window. So you have two processes here. You have x of n, a discrete version, and you have a time window which keeps moving with you, right? Same window size. So the window size is here Q plus 1, because you're using the current value and Q, the current value and where is it? Current value and Q previous values, right? So for example, the stock values are like this. Okay, a 30-day window. You take a 30-day, smooth it out. So you take all the values over the 30-day, average it, you are going to get one value. So you take, then you move the window. So you're going to see a smoother version. So you can work with the smoother version rather than this jittery version, right? So this is a moving average version of, so this is your Wn and this is your x of n, right? So the question is, if Wn is a stochastic process, is xn stochastic? If Wn stationary, xn stationary? If Wn has a power spectrum, what is the power spectrum, etc. So that's what we are. But first, if you recall your signals system course, if you do a simple Z transform on both the sides, remember This is delayed version. So if x of n has a transform x of z, then you see, let's look at the ARMA equation itself. So this reads now ak x of n minus k plus sigma bk w of n minus k here k is, you can use two different indices. Here it is not 0 through p because 0 is already here. So putting 0 here, it won't make any sense, because if you put 0 xn equal to xn, so it's k equal to 1 through p. And generally this is a white noise process. That's the modeling used. So the question is, if this process is stationary, is the other one stationary? So if you take a z transform on both these sides, anybody remembers what's the z transform of xn minus k? It's a delayed version. Delay appears, right? So this is equal to minus sigma ak 0 raised to minus k. Plus, how about here? What is the z transform of? Same thing, right? So this is bk z to the power minus k w of z. But you see, I'm going to bring this term to this side, because there is also an x of z here, right? So if I bring it to one side, this reads now. See, you can see otherwise this would be a minus, because I had minus here. This would be sigma akz to the power minus k equal to b naught plus sigma, either way, or you leave it alone like this, k equal to 1 through q bk 0 raised to minus k multiplied by wc. So you see, I can write this as x of z equal to something multiplied by w of z. So this is of the form h of z multiplied by w of z, and this something is so you can see this is the denominator, right? So 1 plus sigma ak z raised to minus k equal to 1 through p, and this is b naught plus sigma bk z to the power minus k equal to 1 through q. So this is your h of z. So this looks like a linear time invariant system transfer function. So consequently, I can write that whole thing as an input. Look at what is the input there? If x of z equal to h of z, so if this is hn or h of z, what is the input, what is the output? Anybody? From your
X of z is output, then h of z into w of z output.
So what is the input? Wn, right? So what it suddenly says is the ARMA process has this representation, if you like, a linear time invariant system with a system transfer function given by which is a polynomial b naught plus b1 z inverse etc. up to bq z to the power minus q, and here you have ratio of two polynomials. Look at this. This is the ratio of two polynomials in the variable z inverse, which represents 1 unit of delay. So this is a rational transfer function. So now what is the answer? If this is Whiteson stationary, what about x of n? Anybody? Yeah, because it's a linear time invariant system. This is actually a perfect example of a discrete case. This has got some inverse transform in the time domain h of n. Anybody knows how to? You must have learned how do you find h of n? Anyone? Look at here. How many poles are there? So let me write the poles as 1 minus alpha k c raised to minus k product. How many poles? Huh? All right, so this goes here. And in the numerator, it was whatever it was. There is a b naught plus b1. Of course, there are how many zeros are there? Q zeros. So you know an ARMA system has Q zeros and P poles, whatever are those values. So this is. Now you also have, you know that you can write this as what? If you have a, you can write it as a partial fraction, right? So what would this be? This of course can be written as, I'm going to assume that all these poles are a symbol. There could be multiple poles, then it's a little complicated. Otherwise you can, right? This is true. Let me assume that Q is less than P. And for the time being, I'm assuming Q is less than P. Then it is certainly true, right? If this degree is less than this, you get a proper partial fraction. Otherwise, you pull out that term. Anybody knows how to do this? All right, so from here you can find out Hn. What is the inverse transform of this? So easiest way is, maybe look at the other way. If you have a system h of n which is a to the power n, let's say a absolute value of a is less than 1 for n positive, then what is h of z? So remember, I'm saying that if you look at the impulse response, it's like this. That's what it means, right? So it goes all the way, or h of k. So this is sigma h of n z minus n, right? N equal to 0 through infinity, because it's given that h of n is 0, otherwise it's a causal system, h of n. So this is now summation. Hn is a to the power n, so I can write it as az inverse to the power n equal to 0 through infinity. How do you sum this? Anybody? This is a geometric series, 1 upon 1 minus az inverse. Look here, each of our term looks like that, right? So from here you can conclude what? H of n is, what is the inverse transform of this? Each one term. Remember, of course, I can multiply by an ak that will be there. So this is ak multiplied by there are p poles, and n goes from 0 through infinity, and this is 0 n negative, right? Right? That's the impulse response. So that's a linear time invariant system with the impulse response. So we know that if this is Whiteson stationary, this is Whiteson stationary, they are jointly Whiteson stationary. The output is Whiteson stationary also. So consequently, if the input has some power spectrum, what is the power spectrum of the output? Anybody? So you have all these relations. Rx is, remember, W. Rx, W, K is, I've already concluded it is Whiteson stationary. So this will be RW, WK convolved with what? Anybody? Input autocorrelation convolved with? Right, minus K. And RXX K or N is RW cross spectrum convolved, cross correlation convolved with H of K, which is the same as the input autocorrelation function convolved with H of K convolved with H of minus K star. All right, so from here, of course, we know that the power spectrum of the output is the input power spectrum and
h omega square.
yeah, not h e raised to j omega, right? This is the DTFT of the impulse sequence, right? In Z, here you replace Z by not j omega, right? The way you said h omega, we are not replacing Z by omega. Z by what? What do in the discrete case? How do you find? How do you translate this into DTFT? E to the power j omega, right? That's the so that's what the squared, right? So this is the relation. So this is the most general case. What is an AR case? Anyone? AR case is when Q is 0. There is no moving average piece. So look at here. So ARP is xn is minus sigma ak x of n minus k equal to 1 through p plus wn. So your HFC, or you don't have to go through all this. HFC now simply looks like this. So this is an ARP. You can also call it to be an all-pole model. Only poles, no zeros. So if your data has this form, then it is an AR process, just autoregressive. So that was the homework problem, right? And if it is just to complete the discussion, if a process is, so this is x of n. When you say x of n is, or x of n is AR, this is what we mean by. And of course you can put in all the other things. So the power spectrum of this is this system transfer squared multiplied by the input spectrum. If input happens to be white noise, that's sigma squared, right? So this is MAQ means xn is of this form, sigma bk, what is it, w n minus k equal to 0 through q. And here of course h of z is simply a bunch of delays, right? bk z raised to minus k equal to 0 through q, right? We just, because put p equal to 0 here. Remember, all you need is this. Put q equal to 0, you get 1 over polynomial. Put p equal to 0, you just get the numerator divided by 1, which will be moving average. So it's used in statistics a lot, autoregressive moving average processes. So if you see a phenomenon in nature, so it may come to your, a good question to ask is, can I approximate or represent that natural phenomena by an ARMA process? Then of course the question is, what should be, these are called the model order. So take for example weather also. Daily weather, you say there are 27 factors involved. So is it possible to represent it by 27, a system with 27 parameters or 55 parameters? Then you are looking at, so maybe there are regression coefficients which are a certain number, and there is also another phenomena going on with a certain number, both moving these two combined together. So bottom line is, for an ARMA process or an AR process, if the driving phenomenon, if it is stationary, then the output is stationary. If this is not stationary, then this is not stationary. Okay. As a rule, mostly, though we have seen rare exceptions, right? And the power spectrum is of course given by this. So you know what happens with the, so remember, if you have this system, you can plot h of z, right? So suppose h e raised to j omega in frequency domain. Remember, this you can plot without knowing what is the input, because this is just a system characteristics. So of course, remember somewhere here, if the input is white noise, and then this is simply sigma squared, and all the characteristics of the output process that you are interested can be studied by looking at this. So if I plot it, and if it happens to have, see, a characteristics like this, for example, okay. So this is omega. Already you can say certain things. What happens at this frequency? What do you suspect? Hello, looking at the picture. Omega 1. Huh? What is it here? So remember, I only have this picture. This is h omega squared. So let's say the picture is like this. Omega 2 is what? Remember, this is frequency. This is versus power. So if you excite the system with some system, whatever is the power at this frequency, see, nothing is going to go through. So this is what? 0. So that will be a this is going to tell you something about these coefficients, right? And similarly, this will be a pole, and that's going to tell you about the denominator coefficients. So if you can, for example, figure out all, so if you plot this patiently for all frequencies, and let's say later it goes like this. So then if you look at the system carefully, this will tell you how many, so for example, this is saying that for large frequencies, this is going down. So this is already going to tell you that the number of poles versus zeros, etc. So right. So large frequencies, the denominator must be taking over because the denominator is becoming larger, and it's driving to 0. Similarly, this is a frequency where show is stopped, nothing goes out. So this is a characteristics of the system, and so the power for this process at here. So by plotting this quantity, the output power, you can tell a lot about the system that's behind the process. So that's the usefulness of a quick introduction to, there is more we can talk about this. For example, how are the autocorrelations related, etc. So for example, I guess you have, for example, take this. You can try to find out the output autocorrelations and see the relations between those, etc. Any other questions on this? So Whiteson stationary leads to Whiteson stationary. And output spectrum is the system transfer function squared multiplied by the input power spectrum. So the important thing is for an ARMA system, it has got a set of numerator coefficients which are zeros and a set of denominator coefficients which are poles. And they show you they define the frequency characteristics of the system, which is characteristic of the output process. Of course, if the input process is not white noise, then its spectral shape is also going to contaminate this, right? I mean, this spectral shape multiplied by this spectral shape will give you the output spectral shape. All right, so what else should we review?
I have a question here. So do you mean like the regressive moving is also regressive is kind of like the signal itself, and the moving average is some kind of noise?
Right, so you could say that, that's true. So you have a driving noise process, that's your WN, right? So maybe you ask the question again, let me.
So I think because at the very beginning you said xn equal to the sum of something like ak times xn minus
Yeah, here,
k.
right here.
Yeah.
This, yeah.
Yeah, like that, and plus omega n, and the other term is like the sum of.
BK, not omega, BKW n minus k.
Okay.
So you have two processes here.
Okay.
You can think of this as the driver or noise process, and this is the phenomena that you are interested. Okay. So it's definitely, you can see this is one way to say is this is random because this is random. And but even though it is random, it has some structure behind it. The structure is that current value depends on P previous values, and also it depends on a certain amount of previous values from the driving noise also. And so if you take special cases, you get AR and MA. So the assumption is if Wn is white noise, look at the top line here. If Wn is white noise, remember this is the current value, right? So this current value is not going to affect the previous, the current value is only going to affect the current value of xn, right? So the current value is not going to affect the previous values of xn, right? Because this noise is coming up. So you can use that to derive the autocorrelations of the output process, etc. So we have already established, so if this is White's and stationary, this is already White's and stationary, right? So Rk, which will be expected value of x n plus k, right? So this you can write it as expected value of, look here, just to show you something quick, minus sigma ak x n plus, so let me write this as m, this is m, that's a dummy variable there, right? So n plus k minus m, right? Plus w of what? W of this value. This value is what? W n plus k multiplied by w of n, right? W of x of n, right? I mean multiplied by x of n star, right? We can expand this, but I am not expanding. This is fine, right? Yes? So this is what? Look at the first term, that's easy. So minus sigma am, m equal to 1 through p. We can do it mentally. Expect two terms are there. First is expected value of this x multiplied by this. Already we know it is White's and stationary. That's the way. This variable minus this variable is Rk. So what will be this quantity multiplied by this expected value? Anybody?
RK minus.
Think again. So n goes away. K minus m. You're right. Yeah. Plus you have expected value of w n plus k multiplied by x of n star. Now listen to the argument. Suppose k is strict, so we have two cases, k equal to 1, I mean k equal to 0 and k strictly greater than 0, right? K strictly greater than 0 means what? K is greater than or equal to 1, 1, 2, 3, etc. What happens, what is the correlation between wn plus k and xn if k is strictly greater than 0? Think physically, why is it uncorrelated? Because look at the last top line. Wn is only coming now. Wn is associated with x of n. Wn plus k is associated with a future value, right? So that's not going to affect, that's, xn has already happened some time back. So what is going to come in future is not going to affect this, right? You see that, right? Wn is here. In terms of time, wn plus k is going to come later, and xn is already here. Then you need xn plus 1, etc. to, this is going to happen later. So this is certainly uncorrelated with this. So this term is 0 here. So you can see that already you can begin to see the structure in an AR process. RKs are, so that's the relation, right? RK depends on minus sigma am Rk minus m, k equal to, m equal to 1 through p. Hold on. So we have to take the case when this is, when k is 0, you have wn and xn. But xn itself is, but again by the same argument, wn is uncorrelated with all the previous values. Wn squared is delta squared, right? So we can write this as, if you want, like this, right? So we can write it in one line. This means that when k equal to 0, there is a sigma squared term here. And otherwise you have, so you can see the Rk itself is depends on the previous values of the Rk. So if you can figure out if you can find out the covariances, you can find out the system parameters from here, and so on, right? Any other questions? You? Hello? Where is your next question?
Haven't figured out.
All right, so this gives you a idea about the
So why is the expense value of at omega n plus 1 times x is 0?
yeah, that's what I'm trying to say. Let's look at xn. Xn depends on w. So you can clearly see xn depends on w. Look here, right? Xn depends on wn, right?
Yes.
Look here. Here you have what? Ak x of n minus k. Then look at xn plus 1. N plus 1 minus k. You see that there is xn here, right?
Yeah.
Why? Because when k equal to 1, you have xn term, right? But xn depends on wn. So you can say the xn plus 1 depends on both wn and wn plus 1, right?
Yes.
But this term doesn't depend on this,
No.
right?
Right.
So this term cannot depend on wn plus k, which is going to come later. So this and this are uncorrelated.
Okay.
Even this and this are uncorrelated. But xn plus 1k depends on wn, because look here, xn plus 1 depends on xn. Xn is here, but xn depends on, so this is a function of both of these.
Okay.
Very good. So if you are looking for, so this is a key relation. If you are looking for all rk's beyond k greater than 0, greater than or equal to 1, then you had infinite set of relations like this, right? So you can, and that's going to determine, do you see this? All right, so let me pull everything to the right, how will you write this? Let me bring this also to this side. So we can write, you see this rk, I'm going to bring this here. So all I need is to make this what? Let's write it properly. So do you see this? So the key relation is for an AR process, sigma AK R of.
So I asked that you write it a little bit more to the left where the black is, because
You can see.
with all that chalk here. It's hard to-
Can you, do you want to pull that thing down?
Yeah, sure.
Other one. Yeah. Maybe one more? Or it doesn't bother you?
No, this one doesn't. All right.
All right, so the key relation is anybody who doesn't see this? Or no one is seeing this? No? Yes? Remember, look here. Previously we had, look at this expression. Rk, let me bring this Rk to this side. Remember, this is gone. So I can put from m equal to 0, 3p. I just rewrote m in terms of k, and instead of k I put n. That's all, okay. So the conclusion is for an ARP process, this is true. If x of n is AR, then its autocorrelations satisfy this. Now you see, I can write this as a huge matrix equation, right? So look here, k equal to a naught is 1, we know, right? A1, A2, up to AP. And here you have all zeros. How many equations are there? Anybody? How many equations? How many? How many equations? What? Look at here. For every n equal to 1, n equal to 2, n equal to 3, all the way to, excuse me,
Okay.
what did you say? 3? How many equations on n? This is n.
Depends how many data we have.
I have all the data you need. So huh?
It can be.
So this is true for all values of n. How many n's are there? The n greater than or equal to 1. Huh?
That could be infinite.
Okay, why is it so much doubt? Look, n is greater than 1 means n could be 2, 3, etc. So let's draw the equation for n equal to 1, n equal to 2, etc. There is no end. So what will be the first, what are the numbers coming here? Look here. You need to get used to n equal to 1. Huh? So R1 then? Remember k equal to 0, n equal to 1. K equal to 1, then R0, then R1, right?
We should start with n greater than.
All right, so that's fine. N equal to, so remember, if it is real, this is R minus 1, you are right. But that's going to be R1 star, right? So R minus 2 up to? R of k goes up to p, and n is 1. So, yeah, p, 1 minus p, or, right, 1 minus p. And then you put n equal to 2. So you will see a pattern here, right? And then you know you can use this. You have how many? So these R's. Remember, this is going to be an infinite set here. These R's have linear relationship among them. So if you take submatrices, you can reduce their rank. Or for example, if you pick up p equations from here, you can solve for the A1 through AP, you can already see. And you can, but you may say, I don't even know the rank. But this will give you the clue. The rank of, if you take any p plus 1 structure in this, the rank must be p. So you can take the p plus 1 structure and try to figure out what the rank is, etc. Right? That's it. So actually there is a little more discussion of this on my lecture 14, so you can read it if you want. So let's just stop this here.